Students, and welcome to day 7 of our virtual instruction for AP Statistics. I hope you got a chance to check in yesterday with my colleague Brendan Murphy, where he talked about confidence intervals for slopes yesterday. And listen, I've got some big news for today. The lesson that we are about to cover today would very likely be the last lesson of the school year. It is at the very, very end of the content. So essentially what you're going to be seeing today is the last lesson of AP Statistics. And then of course, tomorrow, Brandon's going to take you through a couple of AP exam practice questions. And then starting Monday, we are going to jump into AP exam review. So let's go ahead and jump right into what we have here for you today. Just to make sure that everybody is in the right place. You should be in AP Statistics, I hope, if you are here right now. My name is Luke Wilcox. I am an AP Statistics teacher at East Kentwood High School in Kentwood, Michigan. And I do have some other announcements to share with you. If you've already been with us for a couple of days, you've seen these announcements, but we just wanted to be careful in case we have anybody that is new with us. Just want to check in on a couple important ideas here. Let you know some schedule things. Of course, our meeting time, Monday through Friday, this time right now, 2 o'clock till 2:45 Eastern Standard Time. The first set of lessons, which we're just in the middle of, just approaching the end of, is Units 8 and 9. And we've already been all the way through Unit 8. And Unit 9 is actually what we're going to finish today, the inference for slopes. And the most important thing you need to know about Units 8 and 9 is that they will not be covered on this year's AP exam, the 2020 exam. Now, starting Monday, that is Monday, April 6th, we are going to be covering content that will, in fact, be assessed on the 2020 AP exam. So that starts our AP exam review. We will definitely talk more on Monday about the calendar. By the end of the day tomorrow, there'll actually be an official calendar that will get announced from College Board. So you can check to see what every single one of the lessons is going to look like for the AP exam review. Now, in terms of resources, if there is every day we have a lesson, we have a homework problem. If you want to be able to see those or to print those out, you can go to statsmedic.com/YouTube. There is a link. If you look down below, you can click right through to the link. It's organized by day. So you would look for today, Thursday, April 2nd, if you wanted the lesson that we are about to be going through. And then finally, if you are a student or know a student who needs a device or needs access to the internet in order to take the AP exam this year, which will be at home, there is a website here that you can go to, and there you can request a device or request internet access. So certainly, if you have a classmate, a friend, who might need access to technology, please write that down and get that to them so that we want everyone to be able to take the AP exam this year. Okay, so let's check back in with what you learned yesterday with Mr. Murphy. He left you with this homework problem, which is quite a lengthy one. So let's just jump right into it here. Okay, so here's what it says. Windmills generate electricity by transferring energy from wind to a turbine. A study was conducted to examine the relationship between wind velocity in miles per hour and electricity production in amperes for one particular windmill. For the windmill, measurements were taken on 25 randomly selected days, and the computer output for the regression analysis for predicting electricity production based on wind velocity. So I'm actually going to pause right there because they've given away the two variables for this problem. And I think I can identify which one is X and which one is Y, because I know that we are typically trying to predict the Y value from the X value. And in here, they're trying to predict electricity production. That means that's going to be our Y variable. Based on the wind velocity, that's going to be our X variable. Okay, let me continue on here. The regression model assumptions were checked and determined to be reasonable over the interval of wind speeds represented in the data, which were from 10 miles per hour to 40 miles per hour. So I think what they're saying here when they say assumptions were checked is that what we've been calling the conditions, and remember there are 5 of them, those have been met. So we don't actually have to go through and check the conditions, which is kind of nice. So We have our computer output here. Let's identify a couple of things here in the computer output. First of all, I do want you to know that the x variable will always be represented below the word constant, and we actually knew that the wind velocity was going to be the x variable. And then that first column of numbers is going to tell us two things that will likely be very important for us: the y-intercept for the LSRL and the slope for the LSRL. And I hope you learned with Mr. Murphy yesterday that this value right here is one that we just might need. That's what's called the standard error of the slope, or SEB. Now, there are some other numbers there that we haven't really talked about, but I'm hoping by the end of the lesson today that some of these numbers make a little bit of sense to you. So let's jump into part A here. Okay, part A says, use the computer output above to determine the equation of the least squares regression line. Identify all variables used in the equation. Okay, we know our y-intercept, we know our slope. This is easy. It's y equals the y-intercept, which is 0.137, plus the slope, which is 0.240 times x. Now, it does say identify all variables used in the equation, and what they want there is to know what x represents and what y represents. So I actually try to get in the habit, instead of writing x, I'm going to write what x represents, which is wind velocity. And instead of writing y, I'm going to write what y represents here, which we know is the electricity production. So I'm just going to write it as electricity. Now, the other thing that I think is really important here is that we are trying to predict the electricity from the wind velocity. So I'm going to put a hat on top of the electricity, showing that that is a predicted electricity value based on the wind velocity. Okay, let's move to part B. How much more electricity would the windmill be expected to produce on a day when the wind velocity is 25 miles per hour than on a day when the wind velocity is 15? Show how you arrived at your answer. Okay, there are two different approaches to this particular problem. I'm going to show you the long way, and then I'll show you the short way. Okay, the long way is to just go ahead and figure out what the predicted electricity would be for each one of these speeds. So let me start with a speed of 25 miles per hour. And I know I can predict the y value, or the electricity, using the line of best fit. So 0.137 plus 0.240 times the wind velocity. And we want to check that for a 25 mile per hour wind velocity. And that's going to give you about 6.137 amperes is the electricity that would be produced. Now that's for a 25 mile per hour wind. Let's now check it for a 15 mile per hour wind. And all that means is I got to plug in 15 for x this time. So same equation, but now I'm just plugging in my 15, and that's going to give me a value of 3.737. And we want to know how much more electricity was generated on the day with 25 miles per hour. So we just need to take the difference between these two. So I would do, let's see, 6.137 minus the 3.737. And that's going to give me about 2.5 amperes, right? 2.4 amperes. So that would be my final answer. That is the additional electricity from 25 miles per hour than 15 miles per hour. Now that's the long way. I told you there was a short way. And the short way has to do with this value right here, which is the slope of the line of best fit. And if you think about the interpretation of that slope, it tells you for an increase of 1 in x. So for an increase of 1 mile per hour in the wind velocity, we would predict that the electricity would increase by 0.240. Now, that value, that 0.240, is the predicted increase in the electricity if we increase by 1 mile per hour. But we want to increase by 10 miles per hour, from 15 miles per hour to 25 miles per hour. So we would have to take that value and multiply it by 10. And sure enough, you're going to get that same answer of 2.4. So you actually could have justified this in two different ways. You could have used the slope, or you could have just plugged in values into the line of best fit here. All right, let's look at part C. Part C says, what proportion of the variation in electricity production is explained by its linear relationship with the wind velocity? Now, I'm hoping that this one rings a bell. This is an interpretation that you just sort of have to know. It is the variation in y that can be explained by the linear relationship. And what we're looking for there is the r squared value, okay? And you want to make sure that in your computer output, you're picking the r squared value, not the adjusted r squared value. And we see that r squared is equal to 0.873. And sure enough, what that's telling you is that 87.3% of the variation in y can be explained by the linear relationship. And that's really all we need there is a percent. Well, I suppose they're asking for a proportion. So scratch that. We could write it as 0.873 if they ask for a proportion. Okay, last part here, part D. Is there statistically convincing evidence that electricity production by the windmill is related to wind velocity? Now you see this convincing evidence, and that is a very big clue to you that you're going to need a significance test. And we have not yet talked about how to do a significance test for a slope. In fact, that's what today's lesson is all about. So I am not going to answer this question yet. You will see this question again later. So I think that's a perfect segue into today's lesson. We are ready for the lesson overview. This is where I will talk through the learning targets. And then at the very end of the lesson, we will come back to these 3 learning targets just to check to make sure that we hit everything that we needed to. So here we go. Learning target number 1, check conditions for performing inference for the slope of a population LSRL. Well, lucky for us, we've been doing that for a couple of days now, and I think that part's going to go fairly quickly. And then the big one here, learning target number 2, we got to be able to do a significance test for slope. And just like we're getting in the habit of at this point, I'm going to use the 4-step process of state, plan, do, conclude. And then finally, we're going to make a connection between what Mr. Murphy taught you yesterday and what I'm going to teach you today. And that's to make the connection between a confidence interval and a conclusion for a significance test, because they are very closely related. So we will check back in with these 3 learning targets at the very end of the lesson, but I believe we are now ready to jump into today's activity. So here we go. The question of the day today is, does seat location matter? And honestly, this is a real thing that teachers think about, right? We have to make our seating charts. Who should we put where? Who do we sit next to who? And some teachers think, you know, it doesn't make any difference where the students sit. While there are some teachers that think very, very carefully about where they sit their students. And my hypothesis has always been that the front seats, right in the front of the room, those are the best seats in the house, because that's where the best learning occurs. And so this whole experiment was done to see if that's actually true. So let's dig right in and see what it says here, okay? Do students who sit in the front rows do better than students who sit farther away? Mr. Wilcox randomly assigns his students to rows at the beginning of a semester and then measures their exam scores at the end of the semester. Following are the results. So I did this a couple of years ago. This is real data. This is what I found. And you see the scatter plot there. Now, just to be clear about row number here. If you look at this little picture at the top, if this were the front of the room, then I'm thinking that the front rows are the best rows. That's going to be row 1. So I think that row 1 is going to be the best seat in the house, okay? And then we just count backwards from there. So, you know, this is row 2, this is row 3, and so on. Now, I only had 5 rows in my particular classroom, so you're going to see in the data, when you look down here at the x-axis, that that is just the rows there, okay? So let's take a look at the data. Now, the scatter plot here, you can see that we are graphing row on the x-axis. That's our explanatory variable. And the exam score at the end of the semester, that is our response variable. And I think you can see here from the scatter plot that we have a fairly weak negative linear relationship, but there certainly does appear to be a negative linear relationship here, even though it's not super strong. And you can look at the computer output here in order to confirm some of that stuff. And certainly we're going to be needing some of the values in this computer output here. So let's just identify, first of all, that score is our y variable and row is our x variable. We know that this first number that's being given to us is the y-intercept. And we know the second value that's being given to us is the slope. And hopefully from yesterday, you know that this value right here is the standard error of the slope. And we just might need that for some of the work that we're going to be doing here. So as I predicted, you can see from the data that there is a negative relationship. The further back you are in the classroom, it appears the lower exam scores you get at the end. So let's dig into a couple of questions here. Okay, question number one, is this an observational study or an experiment? Okay, definitely for this one, it is an experiment. And the difference between an experiment and an observational study is that the researcher or whoever's collecting the data has to randomly assign treatments to the subjects. And I did assign row numbers to the students, right? I randomly assigned them a row. So we're going to say here the big difference between observational study and an experiment. For the experiment, the teacher or the researcher is imposing a treatment. And I'm even going to identify what the treatment is here. The treatment for the students that they were randomly assigned was a row, right? Each student was randomly assigned to one of the 5 rows. Now, second question related to that, why is it important to randomly assign the students rather than letting each student choose their own seat? So why is it important that we do this? Well, if you think about it, if I just let students sit wherever they wanted to, some people might say that the more studious students who really want to do well would come right up front. And those students that are trying to hide out or maybe want to goofball, they would sit way in the back, right? And then at the end of the semester, if I noticed that the students in the front rows were doing better than the students in the back rows, I wouldn't know if it was because of the row that they were in or if it was because of some other variable, like how motivated they were to learn, right? So that's why we need random assignment, is to help us out with all of these other variables that are there. And the idea is that when we randomly assign students to their row, we're also sort of randomly distributing all of these variables throughout the room. So there might be some super motivated kids that end up in the front and some in the middle and some in the back. But we're sort of evenly distributing them so that each group or each row is roughly equivalent, right? So that the only difference between those groups is the row number. So let me try and capture this. The big idea here is about the purpose of random assignment. And the reason we want random assignment is because it creates roughly equivalent groups, right? So all the students in row 1 and row 2 and row 3 and row 4 and row 5, those 5 groups should be roughly equivalent in terms of all these variables, right? So that if there's a difference in the end, I know that the difference happened because of the row, not because of some other variable. This is what allows us to show causation, right? That the row caused the scores to go down. So I'm going to add that into my solution here. I'm going to say, which allows us to show causation. So there's an important connection that we're making here. This is a really important connection about the purpose of random assignment. And the purpose of random assignment is so that in the end, if we have statistically significant results, we can say that there's some sort of causal relationship between X and Y. Okay, the equation of the least squares regression line. We're getting really good at this. We know what our y-intercept is. We know what our slope is. I'm going to go right to even using the variables. The y variable here is the exam score, and it is what we're trying to predict. So the predicted exam score equals, and then I'm going to go with my y-intercept, 88.07 minus 2.53, that's my slope. And then my x variable here, oops, is the row that they are in. Okay, so my x variable is row. Now I am noticing one thing that I'm going to want you to fix real quick here. This right here, this should not say score. We're going to get rid of that. That should definitely say row. That will always be your x variable there, and we definitely know the x variable here is row. All right, so we got our equation here, the least squares regression line, and we are ready to interpret the slope. Well, the slope here, we know what the slope is. It's negative 2.53. And we've already had some practice with interpreting the slope, so I'm going to go right into it here. For each additional increase of 1 in x, now in this case it's the row. So for each additional row, when we move back one row, the predicted exam score decreases by 2.53 points. Now, just to check in here, why did I say decreases? Well, that's because of the negative slope. And actually, we knew that by looking at the scatter plot, that we have a negative relationship here, right? So for each additional row, that's for each additional x value, make sure you have the word predicted. And then you got your exam score, that's the y value, right? This is my x, this is my y. Decreases by 2.53, and then I've included some units here of points, right? So we do have a negative slope. It appears that each time you move back a row, your exam score goes down by about 2.5 points, right? Now that could make all the difference for your final exam score here. Okay, now we've got two final graphs here, and these are graphs that we've looked at for the past couple of lessons. But the question says, what information does each of the following graphs reveal? Okay, so first of all, let's identify what each one of these graphs is. The first one, of course, is a residual plot. And there's actually some really important information that we're getting from this residual plot. The first of which is that we don't see a real clear leftover pattern. You don't see like a U shape or an upside down U shape. I call it a smiley face or a frown face. You're seeing pretty even scatter above and below. And so I'm going to say no clear leftover pattern. And so what this is telling me is that this relationship that we started with in the scatter plot is somewhat linear, right? We have a linear relationship here. So I'm going to say that this indicates linear relationship is appropriate. All right, that's the first thing. Now, the second thing that's important that we see in the residual plot here is that for each x value, if you look at each one of the x values, the distribution of the y has about the same variability, right? There's like sort of the same spread on each one of these. We're not seeing like a big increase in spread as we move to the right, or a big decrease in spread as we move to the right. So I'm going to say here, for each x value, which is for each row, the variability of the y variable, which is the scores, is about the same. Right? We have about the same variability. So those are the two important things that we get from that first residual plot. Now, the second picture that you see there, you see residuals, but this is not the same as a residual plot, because it's not a scatter plot with two variables. It is one variable residuals. This is just simply a dot plot of the residuals. Now, here's what we want to look for in the dot plot of residuals. We want to check to make sure that we don't have strong skew or outliers, so that it appears that this could have come from a somewhat normal distribution. And certainly it doesn't appear that we have any outliers or strong skew. So I'm going to say no strong skew or outliers. Now, of course, the reason we're looking at these two graphs here is we're setting up for inference for slope. And what we're really doing here is we're checking some of the conditions. So let's make clear which condition we were checking. In this first one, no clear leftover pattern indicates a linear relationship is appropriate. That's going to become the linear condition when we get to the significance test. The second one, for each x, the variability of y is about the same. We're going to call this condition the equal standard deviation condition. And then the third one here, no strong skew or outliers, that's what's going to become the normal condition, right? Which says that for each x value, the distribution of y values is approximately normal. So I think we've done most of the legwork here in preparation for inference, for a significance test. And we are now prepared to do a full significance test, 4-step state plan do conclude. All right, so here we go. Question says, do the data provide convincing evidence of a negative linear relationship between row and score? Now, before we jump right in, let's talk about this idea of convincing evidence. And maybe before we talk about having convincing evidence, we want to check to make sure that we just have some evidence to begin with. So the question is, do we even have some evidence of a negative linear relationship between row and score? And certainly we saw on the previous page that we do have some evidence, right? The slope that we were given is a negative slope. So I'm going to say some evidence because the slope value, which was negative 2.53, is negative, right? It's less than 0. So that's telling me that I do have some evidence, right? But maybe that slope value of negative 2.53 happened purely by chance just because of the random assignment, and row doesn't really have any relationship with exam score. So in order for us to check whether we have convincing evidence, this is why we need a significance test, right? This is what we need the p-value for, is to be able to make a decision about convincing evidence. So let's jump right in. All right, in the state, we're going to start with our parameter. And actually, the statistic here, we just identified the statistic. The statistic is our b value, which is negative 2.53. Now, that is a statistic based on a sample or based on a particular random assignment. The parameter that we're trying to estimate is the true slope for the population LSRL, which we call beta. So let's clearly identify what beta is here. It is the true slope of the population LSRL. And then I need to get some context in here. So I'm going to say for x equals row and y equals score. Right? That's the parameter. And then, of course, we're going to use that parameter to write our hypotheses here. Okay? And the null hypothesis is going to say that there is no relationship between row and score. And we are going to try and find evidence against that claim. Now, here's how we're going to write it. If there is no relationship or no linear relationship between those two variables, then that slope would be 0, right? A beta equals 0 would say that there is no linear relationship. Now, the alternative hypothesis is the claim that we're trying to find evidence in favor of. And in this case, the question says, is there convincing evidence of a negative linear relationship? Well, a negative linear relationship would mean that beta is less than 0. So in words, this would be a negative linear relationship. Now, that alternative hypothesis can be one-sided or two-sided. That's always going to depend on the wording of the question. We've clearly identified from the wording of the question that we want a one-sided, less than 0 alternative hypothesis. Okay, our alpha level is not given to us, so by default, we're going to go with 0.05. Quick note, this is not the same as the alpha, which is the true y-intercept of the population LSRL. This is the significance level alpha, right, 0.05. Okay, let's move to our plan. First of all, the name of the procedure. Okay, this is a one sample procedure, right? We don't have two different samples here. And this is a t-test for slope. So we are going to end up with a t-distribution. When we get down to finding our p-value, we'll need to use a t-distribution for this one. And you did a t-interval yesterday, right, for slope, for estimating slope. Okay, I think we're pretty good with these conditions here. So let's just move pretty quickly through this. For the linear condition, we're going to say that the scatter plot is fairly linear. And I'm going to provide a second justification, which is based on the residual plot. Remember, the residual plot had the even scatter above and below with no clear pattern. So I'm going to say, and the residual plot shows no clear pattern. All right, independent. Well, we know that's the 10% condition, which says that the sample size of 30 is less than 10% of the population of all students. But hold up. Why are we checking the 10% condition? We check the 10% condition when we are sampling without replacement and we're worried about independence. And in this context, are we sampling without replacement? No, this was a problem that dealt with random assignment, not a random sample, okay? So we don't have a random sample here, which means we are not sampling without replacement, which means we do not check the 10% condition here because there is no sampling without replacement, right? We had random assignment here, but we didn't have a random sample. Okay, moving to the normal condition. That's where we check the dot plot of the residuals. And we said on the previous page that dot plot had no strong skew or outliers, which means for each X value, the distribution of Y values is approximately normal. Okay, equal standard deviation. That's where we looked at the residual plot and we wanted to check to make sure that for each X value that the variability was about the same for each one of the Y values. So I'm going to say that it shows similar variability for each X value. All right, and then finally the random condition. We've talked about this one a little bit here. Not a random sample this time, but we did have random assignment. And this is what introduces the variability into the statistic, is the fact that every random assignment would produce a different value for the statistic. So with our condition satisfied, we are ready to actually do a calculation, all right? Now, this is going to look very familiar to some of the work you've done previously in the course. The general formula is always the same. This is given to you on the formula sheet on the AP exam. If we are looking for the standardized test statistic, it is equal to the statistic minus the parameter, all divided by the standard deviation of the statistic, or the standard error most often. So the specific formula here, all right, we know we're going to have a t-test statistic here because this is a t-test. And let's think about the correct notation here. The statistic is the sample slope. The parameter is the population slope. And then we want the standard deviation of the statistic, but in this case, we're going to have to use the standard error of the statistic or the standard error of B. And I think we're ready to plug in some numbers. We already know our sample slope, negative 2.53. Now for beta, we're going to assume the null hypothesis is true. And so we're going to plug in 0, 0 for beta. Now the standard error for B, we need that from the previous page. That is right here at 1.11. So that is my standard error of B, 1.11. And if you plug that into your calculator, you will get a t-test statistic of negative 2.28. So let's go ahead and record that as our test statistic, negative 2.28. We are 2.28 standard deviations or standard errors below the mean. Now for the picture, I'm going to give you two pictures here, the unstandardized as well as the standardized. So let me start out with the unstandardized, which is the sampling distribution of B. And it is approximately normal. And we are gonna assume the null hypothesis is true, which says that beta is equal to 0. So the mean is 0. And then the standard deviation of this, if I were to just use notation, it's the standard deviation of B, or the standard deviation of the sampling distribution of B. Now, the reality is we don't know that, and we're going to have to use our sample to try and estimate that. And so what we do is we use SEB to estimate that standard deviation. And in doing so, when we standardize and we use the standard error of B, the distribution turns into a t distribution, which is a little bit more spread out, not quite as tall. There's our standardized distribution, which is a t distribution. And we need to know the degrees of freedom, which Mr. Murphy talked about yesterday for our two variable analysis is n-2. We had 30 students in this sample, which means our degrees of freedom is 28. There we go. This is a standardized distribution, so 0 is at the center. Now, in order to get the p-value, we need to know how likely is it that just because of the random assignment, we would get a sample slope that we got or farther from what's expected. Now, the sample slope that we got was negative 2.53. So this right here is the p-value that we're looking for, right? Shading away from the center, consistent with the alternative hypothesis less than 0. Now, in the standardized picture, once we standardize that b value, we got a t-test statistic of negative 2.28. And so now this area should be the same as the area in the unstandardized picture. That's our p-value. Now, in order to get that, this is a t-distribution. And to get the area underneath a t-distribution on your calculator, you can use TCDF. And you would give it the lower bound, negative 9999, the upper bound, negative 2.28, and then the degrees of freedom, which is 28. And I'm going to tell you what that comes out as. The p-value here is going to be about 0.015. And I try to get in the habit of making the test statistic and the p-value really stick out, because those are the important things that we need there. So I put a box around those. Now, real quick, look at that t-test statistic and that p-value. And let me go back to the previous page in this computer output here. And I'm hoping you notice something here. Right there, that's your t-test statistic, right? The computer output actually did that for you. And you would think that the next thing over right there is going to be your p-value. But it doesn't match because we had 0.015. But here's the deal. The p-value that you see in the computer output is always a two-sided p-value. Think about it. If we doubled our p-value, there it is, 0.03, right? So the t-test statistic and the p-value are actually given to you in the computer output. All right, we are ready to write our conclusion here. And remember, I always write two sentences for my conclusion. The first is interpreting the p-value. All right, so here we go. Assuming the null is true. In this case, beta is equal to 0. There is a, and then we give our p-value 0.015 probability of getting a sample slope b of negative 2.53 or lower purely by chance. Right? All I'm doing there is I'm interpreting this p-value. It's this area in the curve there, right? So make sure that you have your assuming the null is true, you got your probability, you got your or lower. And then the second sentence, this is probably the one you're more familiar with. This is where we're going to make a decision. Because the p-value, which is 0.015, is less than the significance level alpha of 0.05, we are going to reject the null hypothesis. And we do have convincing evidence. And now I'm just going to go back to the wording of the question here, right? Convincing evidence of, and I've got all this here, negative linear relationship between row and score. Okay, so that concludes the significance test. Now, I do want to show you how you can do this on your calculator. So if you want to grab your calculator, you can do so. If you want to just follow along, you can see on the screen what I'm doing with the calculator. But the calculator will do all of this stuff for you. It's a nice way to check your work. So here we go. Now, the first thing you would have to do is to input the data. So you go to Stat and then Edit. And I've gone ahead and already put the numbers in. So you see all of the rows in list 1 and all of the scores in list 2. And then I go to Stat Tests. And if you scroll way down, you're looking for the linear regression t-test. So there we go. The linear regression t-test here. If you hit enter, it's going to ask you where you put your x and your y values. Then it's going to ask you for your alternative hypothesis, and I've got it at less than 0 here. You can leave this one blank, and you can go right to calculate. And sure enough here, we get our t-test statistic, which matches with what we had in our calculation, and then the p-value, which matches with what we had, along with some other things, the degrees of freedom, the y-intercept, the slope, standard deviation of the residuals, even your r-squared and your r values are given to you there as well. So this is a great way to check your answer. Now, the other nice thing that you have on your calculator, which I know is coming up in the next question, is to do a confidence interval. So I'm going to go down now to linear regression oh, I'm sorry, test. Let me go over to test. I'm going to find the linear regression T interval, which is right below the test. There's the test. There's my T interval. It's going to ask you for the same things, right? Which lists? I'm going to want a confidence level of 95%. And I'm going to hit calculate. So go ahead and write these numbers down. We got negative 4.805 and negative 0.2615. That is our confidence interval. So I want to jump back into the activity here, and let's just finish up with this confidence interval and see if we can see the connection between the confidence interval and the significance test here. So here we go. Last question. My confidence interval, which I got from the calculator, is negative 4.81. I'm going to round it a little bit to negative 0.26. That was my confidence interval. And we want to show that this is consistent with the significance test. Well, if I were to interpret this interval, I would say we are 95% confident that the true slope of the population LSRL is between negative 4.81 and negative 0.26. Now, these are all of the plausible values. And what I notice here is that all the plausible values are negative, right? So we're fairly confident that this slope is negative. And the value that I don't see in there is the null hypothesis value, which is 0, or any positive values there. So clearly we think there's a negative value here. So the decision we would make, because that 0 is not contained within the interval, and I'm going to write this down, because 0 is not in the interval, that means we don't think 0 is a plausible value, and we would reject the null hypothesis here, right? Because the null hypothesis says that beta is equal to 0. And sure enough, reject the null hypothesis is precisely what we said when we did the significance test. Now, just to be clear, when you're making this connection, you should really be making it with a two-sided test, right? And we had a one-sided test, but if you think about it, the two-sided test would have given a p-value of 0.03, and we would have made the same decision, right? Reject the null hypothesis. So whether we use a significance test or a confidence interval, in either case, we're going to reject the null hypothesis. Okay, I think we are ready to try and summarize what we learned here. I'm going to go back to the 3 learning targets that we started with at the beginning. So let's start with the conditions. So learning target number 1 is the conditions. I'm hoping at this point, after a few days of doing this, you feel pretty comfortable. You know the acronym. LINER is going to remind you of what your 5 conditions are. That is the linear condition, the independent condition, or the 10% condition, only if you're sampling without replacement, the normal condition, the equal standard deviation condition, and the random condition. So I'm hoping those feel pretty comfortable for you at this point. Learning target number 2 was to be able to do the significance test as a full 4-step. I'm just going to highlight a couple of parts of this. Okay, first of all, the null hypothesis is going to say there's no linear relationship, beta equals 0. Now the alternative hypothesis could be one-sided or two-sided depending on the wording of the question. So it might be beta is greater than 0. It might be beta is less than 0. It might be beta does not equal 0. You got to look at the wording of the question for that one. All right, the other thing that I think is important in this 4-step process is the formula that you need for this. So we know the general formula for a test statistic is statistic minus the parameter all over the standard deviation of the statistic, or the standard error. And for us, it's going to be a t-test statistic here. We're going to use the sample slope b minus the population slope beta all over the standard error of b. And I'm going to point out a couple of things here. This value is most likely going to be 0 from the null hypothesis, right? And this value right here, it's not likely you'll have to calculate that. You'll be able to get that right from the computer output. And then we've got our last learning target number 3, which is to connect the confidence interval to the significance test. So here's the deal. You're always looking for the null hypothesis value when you make a confidence interval. If it is not in the interval, right? Which was the case here. If it's not in the interval, we don't think that that is a plausible value, and we will reject the null hypothesis. Now, on the other hand, if that null hypothesis value is in the interval, well, then we think that it is a plausible value, and we fail to reject the null. And I guess I'm going to make a little point here. This is for a two-sided test, right? If you're comparing confidence intervals to significance tests, you want to make sure you're looking at two-sided tests. Okay, that brings us to the final question here, which is the check your understanding. This is your homework problem. Should look pretty familiar to you. We may have even talked about it earlier today, but you're going to answer the final question of this, right? And Mr. Murphy will check in with you on this one tomorrow. I appreciate y'all checking in today. I hope you learned something. If you feel like you got something out of today's lesson, make sure you give me a thumbs up down there. That'd be excellent. Please check in with Mr. Murphy tomorrow. He'll be doing some AP exam practice with you. And then I will see you again on Monday when we officially start our AP exam practice. Have a good night.